Have you ever been, like, absolutely certain you knew the most efficient way to do something?
Oh, yeah. Totally.
I mean, maybe you have this specific workflow you use for triaging servers or, an intricate architecture pattern you just always reach for. Or even just a tiny snippet of code you've written, like 100 times.
Right, and you're completely convinced you've optimized it perfectly.
Exactly. You're
Yeah.
so sure. But then, months or even years later, you actually look at the telemetry or you run a profiler and you realize you were actually doing it the hard way all along.
It is a shockingly common trap, especially for experienced professionals, honestly.
Yeah.
Oh, absolutely. We cling to these assumptions about efficiency. We build these massive mental models around what constitutes a quote-unquote best practice, and then we just universally apply those patterns everywhere.
Without even thinking about it.
Right. We rarely pause to empirically verify if those assumptions actually hold up under microscrutiny.
And that tension, right, that friction between what we assume is highly optimized and what the machine is actually doing under the hood, that is the core of what we are getting into today.
It's such a great topic.
It really is. So we're pulling from this incredibly insightful piece by Aaron Rose. It was published on tech-reader.blog, and it's called The Secret Life of Go, Benchmarking.
And I have to say, it is a fantastic deep dive in its own right. Like Aaron Rose framing the mechanics of the Go compiler inside this very relatable, very human narrative.
Yeah, the story aspect is great.
It really makes the technical reality of benchmarking so much more tangible.
Definitely. And just to be clear with you listening right now, the mission of this deep dive isn't merely to review Go syntax.
No, not at all.
We are exploring the very real, very dangerous trap of relying on intuition over empirical measurement. We're going to look at how modern compilers optimize code, how they can completely deceive your benchmark,
Definitely can.
and how to outsmart a machine that might just be, a little too ruthless for its own good. Okay, let's unpack this.
Sounds good. So, the source material opens by setting this vivid scene. It's in a beautiful Beaux Arts library in Lower Manhattan, and we meet two developers.
Okay.
There's Eleanor, who is a senior software engineer, and Ethan, her junior colleague. And Ethan is currently deep in the trenches of a pull request review.
Like aggressively typing. Right.
Yeah, aggressively typing out a defense of his code. He is locked in this classic developer debate with a coworker over how to concatenate two small strings.
Just joining two strings together.
Exactly. Specifically, he's taking a prefix like user and appending an ID number to it. Simple stuff.
Right.
His coworker suggested he just use the standard string concatenation operator, just a simple plus sign.
Makes sense.
But Ethan is vehemently defending his own approach. He used a tool called a strings dot builder.
Oh.
And he actually tells Eleanor that it is objectively the superior pattern because it avoids allocating new memory every time you append.
Okay, I mean, I get where he's coming from. Using a strings.builder to join two tiny strings, it's like, let me think of an analogy.
Sure.
It's like renting a heavy-duty dump truck just to carry a single paperback book across the street.
That's actually a really good way to put it.
Right, like, yes, the dump truck is objectively superior for moving heavy loads all day long, but for one book, it's massive overkill.
It totally is. But to be fair to Ethan, he isn't just pulling this out of thin air.
Right, he read it somewhere.
He's relying on a well-known paradigm in Go, because in Go, strings are immutable.
Right, you can't change them.
Exactly. They're essentially read-only byte slices. You cannot simply modify a string in place to make it longer.
Because if you try to append to an immutable string, the Go runtime has to, go out, allocate a brand new backing array in memory, copy the old bytes over.
Copy the new bytes over.
Yeah, and then leave the old array for the garbage collector to eventually clean up. It's a whole process.
Precisely. And if you're doing that repeatedly, say, I don't know, building a massive JSON payload inside a loop with tens of thousands of iterations.
That would be bad.
Using the plus operator there will cause massive memory fragmentation. The garbage collection pressure would be huge. The application would basically grind to a halt.
Right, so a strings.builder is designed specifically to mitigate that.
Exactly. It maintains a single dynamically growing internal buffer. You append to the builder, and it manages the underlying memory allocation far more intelligently. It only expands when absolutely necessary.
But I think this is where Ethan's intuition really misleads him, right?
How so?
Well, let's look at the actual context of his PR. He isn't building a massive JSON payload in a loop. He is joining exactly two tiny strings exactly one time.
Right.
So going back to the analogy, it's like handing an accountant a single $1 receipt, but forcing them to boot up a massive enterprise accounting software suite just to log it.
Right, right.
Yes, the enterprise software is objectively superior for managing a multinational corporation's finances, but for one receipt. The overhead of just logging in is totally disproportionate to the work being done.
That analogy perfectly isolates the problem. I mean, Ethan's logic is sound at the macro level, but his assumptions are entirely wrong at the micro level.
Yeah.
And this is a trap that senior engineers fall into just as often as juniors, by the way.
Oh, absolutely.
We learn a design pattern, we verify that it scales beautifully, and then we just apply it blindly everywhere. We assume that because the complex tool is the most powerful, it inherently must be the fastest way to process anything.
Which just isn't true. So Eleanor overhears him complaining about this coworker and intervenes. She says, and this is a great quote from the piece, "Performance in Go is a science, Ethan, not a philosophy."
I love that line.
It's so good. She says, we don't argue about performance based on intuition. We measure it.
Exactly.
Okay.
So they decide to settle the debate empirically. They open a new file, string_test.go,
Okay.
and they utilize Go's built-in testing framework. Specifically, they use testing.b for benchmarks.
Right, because standard tests just check if code works, but benchmarks check how fast it is.
Exactly. And this framework, it doesn't just run your code a static number of times. It dynamically scales.
Oh, interesting.
So Ethan writes a for loop, but the limit of the loop is defined by a variable called b.nn.
Okay, let's talk about the mechanics of b.n for a second.
Yeah.
Because it's not just a random number, right?
No.
It scales dynamically to overcome the physical limits of the operating system's clock.
That is the core mechanism, yeah. Because think about it, most operating system clocks have a resolution of maybe a microsecond or a millisecond.
Right.
If the operation you are testing only takes a few nanoseconds, the clock literally cannot tick fast enough to measure a single execution.
It's like trying to time a race car with a sundial.
Basically. So the test runner starts by running the loop a small number of times. If the total time is too short to be statistically significant, it geometrically increases b.n.
So it goes from 1 to 100 to 10,000.
Or millions, yeah.
Yeah.
It just keeps scaling up until the loop runs long enough to provide a mathematically reliable average of nanoseconds per operation.
Okay, so Ethan writes the benchmark. He's testing his strings.builder against the simple plus sign approach. He runs the benchmark command in his terminal, the output appears, and it says both approaches take 0.2 nanoseconds.
Yep, 0.2 nanoseconds.
Less than a billionth of a second. They are exactly the same speed.
They are identically fast.
And reading this in the article, I have to admit I hit a mental roadblock.
The results are certainly jarring.
But wait a second, a billionth of a second. Is Go just magically fast, or is something fishy going on here? Like, let's look at the physics of that for a second.
Let's do it.
A modern CPU running at 3 gigahertz completes about 1 clock cycle every 0.33 nanoseconds.
Right.
So an output of 0.2 nanoseconds implies the CPU is executing a memory allocation, a string copy, and a struct instantiation in less than a single clock cycle.
Which is impossible.
Right. That physically doesn't make sense. So is the benchmark framework just hallucinating?
Well, the framework isn't hallucinating, but it is being aggressively manipulated by the Go compiler.
Ah, okay.
When Eleanor looks at the screen, she immediately diagnoses the issue. She tells Ethan he just fell into the dead code elimination trap.
Here's where it gets really interesting. Dead code elimination. I mean, that's a standard compiler optimization. But how did it completely bypass the benchmarking framework?
To understand how it bypassed the framework, we really have to look at the compiler's static single assignment pass, or the SSA pass.
Okay, the SSA pass.
Right. Because a compiler's job isn't just to translate code into machine language, it's to optimize it. And the Go compiler is famously ruthless about this.
Ruthless how?
Well, it constructs an abstract syntax tree of Ethan's code, and it traces the life cycle of every single variable.
Oh, I see. And in Ethan's benchmark, he was executing the string concatenation,
Yeah.
but he assigned the final result to the blank identifier.
Yes, the underscore character.
Right.
And in Go, the blank identifier explicitly tells the compiler, I don't care about the result of this operation. Discard it.
Oh, wow. So the compiler sees that.
Exactly. The compiler's SSA pass looks at the loop, sees the string operation, and then traces the result to the blank identifier.
Right.
So the compiler makes a strictly logical deduction. It says, if this program never utilizes the output of this mathematical or memory operation anywhere else, Why should I waste CPU cycles actually executing it?
It's like handing an accountant a stack of receipts and telling them to tally it all up, but warning them the final report goes straight into the shredder anyway.
That's a great analogy.
A ruthlessly efficient accountant won't even pick up their calculator. They'll just immediately hand you a blank piece of paper.
That is the exact mechanism. The compiler completely strips the string operation from the final binary. It just deletes the code entirely during compilation.
That's wild.
Yeah.
But wait, if the compiler is smart enough to know the code is useless, why doesn't it just throw a compilation error?
What do you mean?
Well, Go is famously strict about unused variables, right? Like, if I declare a variable in Go and don't use it, the compiler outright refuses to build the application.
That's true.
So why the double standard here?
Because Ethan didn't use a named variable. If he had assigned it to a variable named x and never used x, the compiler would indeed throw a hard error.
Oh, I see.
But he used the blank identifier. He explicitly authorized the compiler to discard the result. It's not an unused variable error. It's an intentional discard that the compiler leverages as permission to aggressively optimize.
Wow. So when Ethan ran GoTest, he wasn't benchmarking the strings.builder.
Nope.
And he wasn't benchmarking the plus sign.
No.
He was benchmarking an absolutely empty for loop.
Exactly.
The computer was just spinning its wheels, doing nothing.
Yeah.
Which is why it took 0.2 nanoseconds. It was just measuring the overhead of the loop iterator itself.
Precisely. The compiler outsmarted the developer, but of course this leaves them back at square one.
Right, because the intuition debate is still unresolved.
Yeah.
The empirical measurement was compromised.
Yeah, which means they have to trick the compiler. They have to force the compiler's SSA pass to keep the code intact. And this is where the article introduces what it calls the architect's fix.
Right, because if the compiler is smart enough to delete unused code, how do you trick it into thinking the code is essential?
So Eleanor modifies the benchmark using the global variable trick.
Okay.
She goes outside the benchmark function entirely and declares a package-level global variable. Let's just call it var global result string.
Okay, so it's a global variable now.
Right. Then, inside the b.end loop, she takes the result of the string concatenation and saves it to a local temporary variable. Let's call that local result.
Got it.
And then, and this is the crucial part, she assigns local result to global result. But she does it after the b.end loop has completely finished running.
After the loop, okay.
What's fascinating here is how this exploits the compiler's limitations around cross-package boundaries and escape analysis.
Oh, this is cool.
The Go compiler is brilliant, right? But it analyzes code package by package. When it sees that the output of the string operation is eventually being written to a public package-level global variable, it hits a wall of uncertainty.
Because it can't mathematically prove that some other package somewhere else in the larger application won't eventually try to read that global variable.
Exactly. The compiler is forced to be conservative. It must preserve observable side effects. It says, I cannot guarantee this variable is dead code, therefore I am forced to compile the actual string operation into the binary.
And just like that, the trap is disarmed.
Yep.
But I want to push back on her placement of that assignment for a second. Why assign it after the loop? If the goal is just to trick the compiler, why not just say global result equals string A plus string B directly inside the loop? Wouldn't that be simpler?
Well, it would be simpler to write, sure. But it would completely ruin the benchmark in a different way.
How so?
If you write to a global variable inside a tight loop millions of times, you are forcing the CPU to write out to main memory, or at least constantly invalidate the L1 and L2 caches across different cores.
I see. Writing to a global is a comparatively heavy memory operation.
Very heavy.
So if you do it inside the loop, you are no longer benchmarking string concatenation. You're benchmarking RAM latency and cache coherence.
Spot on. By holding the result in a local stack-allocated variable during the loop, the CPU can just keep overwriting a really fast register.
Right.
Then, once a benchmark timer stops, you do a single flush to the global variable, just to satisfy the compiler's escape analysis. It isolates the specific mechanism you're trying to measure without introducing architectural overhead.
That is an incredibly elegant workaround. You're leveraging the compiler's own strict rules for safety against its desire to aggressively optimize.
It's very clever.
So, with the compiler successfully tricked and the cache overhead avoided, Ethan runs the benchmark one more time.
And this time, the machine actually has to do the heavy lifting. The operation takes measurable time.
The empirical truth finally prints on the screen. And drumroll, the standard string concatenation, just a simple plus sign his coworker suggested, was almost 4 times faster than Ethan's strings.builder.
4 times faster. It wasn't even close.
So what does this all mean? I mean, we spent all this time establishing that strings.builder is highly optimized for memory management.
He did?
It prevents GC churn. It prevents backing array reallocations. Why did it lose so spectacularly here?
Because of a highly specialized optimization deep within the Go runtime.
Oh.
Yeah. When the compiler encounters the plus operator used for exactly 2 strings, it doesn't do a generic memory allocation. It routes that operation to a specialized internal function called concat strings.
And what makes concat strings so much faster?
Well, the runtime takes the 2 strings, pre-calculates their exact combined length, and executes a single perfectly sized memory allocation.
Wow, okay.
It then copies the bytes from the first string, copies the bytes from the second string, and returns. That's it. It is an incredibly lightweight linear process.
Whereas the strings.builder,
Yeah.
even for 2 tiny strings, carries a massive structural tax.
Yes, huge. To use strings.builder, the runtime must instantiate a new struct on the heap or stack. It must initialize an internal slice.
Right.
It requires executing multiple method calls like writeString, which have their own call stack overhead. It has to perform internal capacity checks to see if the buffer needs to grow. It's doing a lot.
Going back to the analogy, it's the cost of renting the dump truck. You had to fill out the paperwork, pay the deposit, start the massive engine, navigate it out of the lot, all just to move one single receipt across the street.
Exactly.
The structural overhead completely eclipses the actual work being done.
It really does.
Yeah,
So Ethan is forced to eat a large slice of humble pie.
I bet.
The article notes that he immediately goes back to his pull request, deletes his whole paragraph defending the objectively superior pattern, and quietly reverts the code to a simple plus sign.
As you do. Yeah.
He looks at Eleanor and admits, "I assumed I was outsmarting the compiler."
And Eleanor replies, "We all do until we run the benchmarks."
It's such a perfect resolution, and if we connect this to the bigger picture, the architectural lesson here is just paramount.
Absolutely.
Performance is entirely empirical. Your intuition about how a system scales is a great starting point for forming a hypothesis, but it is a terrible substitute for data.
Right.
When dealing with the micromechanics of a system, context is everything.
And that context extends so far beyond just writing Go code.
Yeah.
I want you to think about how this applies to the systems you interact with every day.
Oh, it applies everywhere.
Right. Whether you're designing a cloud architecture, optimizing a logistics supply chain, or even just like implementing a new productivity framework for your team. Your deeply held assumptions about efficiency might be completely backward if you aren't actually measuring the empirical results.
We all harbor these deeply defended, universally applied paradigms. We insist on using the complex tool because we want to feel like we're operating at a high level.
Exactly. We implement these heavy, convoluted processes and defend them, just like Ethan did. But are we actually increasing throughput? Or are we just spending all of our processing power managing the overhead of the system itself?
That's the real question.
We have to be fiercely vigilant against our own personal dead code traps.
Because measuring the wrong thing is often worse than not measuring at all. It gives you a completely false sense of security.
It gives you the illusion of optimization. If you're measuring how many hours you sit at your desk or how many internal emails you send, you might feel incredibly productive.
Even if the actual output, the code that ships or the product that launches is 0.
Exactly. You're just spinning an empty for loop in your own life.
That's a brutal way to look at it, but it's so true. And this raises an important question about where the tooling is headed next.
Oh, for sure.
We're currently analyzing a compiler that is already ruthless enough to silently delete dead code just to save a few nanoseconds.
And that leads to a fascinating and maybe slightly unnerving final thought. We know artificial intelligence is rapidly becoming integrated into development environments and compilation pipelines.
It's happening fast.
Right. So what happens in the near future when these AI-driven compilers evolve beyond just recognizing dead code?
They will likely begin recognizing intent.
Right. Will tomorrow's compiler look at a developer like Ethan, see him trying to boot up a massive strings.builder just to join 2 tiny strings, and simply intervene?
I mean, probably.
Will the machine realize he's using a dump truck to move a paperback book and silently, automatically rewrite his code into the optimized plus sign version on the fly?
It's the logical next step, really. If the compiler's telemetry knows the empirical truth better than the human's intuition, the compiler will just quietly correct the human's philosophy.
And if our tools start fixing our bad intuition automatically behind the scenes, abstracting away the micromechanics entirely, Will the act of human benchmarking eventually become a lost art?
It's something to think about.
Will we even know what the machine is optimizing anymore? Keep that in mind the next time you are absolutely certain your way is the fastest. You might just be relying on a mental map that hasn't been empirically benchmarked in a long, long time.